so we can get going for the last session of the day. So we'll be back to Max Metlitski, talking about anomalies, topological theories from a condensed matter perspective.
Okay, so recall last time we started talking about gap phases, and we introduced a class of gap phases which we called invertible. So these are kind of the simplest gap phases, which are almost trivial but not quite. And what we said is that in general these gap phases, they're gapped in the bulk, but they'll have interesting boundary states. And we started discussing perhaps the simplest example of an invertible phase, which is a Kitaev chain in 1 plus 1D. So this is a system of fermions. Here is a Hamiltonian. We saw that the bulk was indeed gapped, but on the boundary there were these dangling Majorana modes, such that effectively the fermion parity of the chain was given by this expression in terms of the boundary Majoranas, and it can take values plus or minus 1. So those two states of the open chain are degenerate. Okay. So the plan for today is to finish the discussion of this model, including how to describe it in continuum field theory, how to compute partition functions on arbitrary space-time manifolds, and then we will mention some other examples of invertible phases in low dimensions, and finally, if we have time, we'll start talking about symmetry. Remember, up till now, I have not imposed any symmetries on my Hamiltonians. The only exception is that when I have systems of fermions, I always have fermion parity. Fermion parity is unbreakable, so I'm not even going to consider it as a symmetry. Okay, so let's go back to the Kitaev chain. One comment that I'd like to make is that, well, actually, let's keep it here. One comment I'd like to make is that, remember, we had this notion of addition of two phases, of stacking. So what happens if I take Kitaev plus Kitaev? Right. So what happens if I just take another one of these chains? And I stack one on top of the other. Well, okay. So now on each boundary, I have a pair of Majoranas. Let's call this gamma 1 prime and gamma and bar prime. So now, if I don't impose any additional symmetries, I can clearly gap out the boundary. Right? I can add delta H equal I gamma 1 gamma 1 prime plus I gamma 2 prime, and this is going to give me a completely gapped spectrum even on an open chain. Right? So from this, you might suspect that actually Kitaev plus Kitaev is trivial. Right? There are no protected edge modes, and that's indeed the case. It's here's a take-home exercise. Show that well, let's even do it on an infinite. Let's even do it on a circle. Show that you can go from the Kitaev chain. From two copies of Kitaev chain to a trivial chain, to two copies of a trivial chain without closing the gap. Remember, the trivial chain was the one that had Majoranas paired up. Well, let me not erase. Let me draw separately. Yeah. So this one moves. Yeah, okay. Okay. So here are my two chains. Well, let me even. I can think about system on a ring. So as a take-home exercise, show that you can go from this state to a state where you pair another color, where you pair like this. Right, this was the trivial state without closing the gap. Yeah, think about it. The idea is basically that you start with these squares, and on each square you can go from this horizontal configuration to a vertical configuration without closing the gap. And then so you first go to vertical, and then you unfold. Think about it. All right. So Kitaev plus Kitaev is trivial. So there is these phases. This Kitaev wire generates a Z2 factor in the classification of one plus one dimensional invertible fermionic phases, and in fact turns out that this exhausts all the 1 plus 1 dimensional invertible fermionic phases. Okay. So that you can prove using matrix product representation in one plus one dimensions. We'll see another kind of argument from field theory why this is all you can get. But okay. So far I am coming back to a single copy of Kitaev wire. So far I'm characterizing the non-triviality of this phase by existence of protected edge modes. But I can ask, is there some way that I can distinguish the Kitaev wire from a trivial wire without cutting it open, just on a closed ring? And the answer turns out to be yes. Distinguish on a ring. The answer turns out to be yes. The answer is the following. Let's take my Kitaev wire, and let me imagine I have the fermion parity symmetry, right? So I can always insert a flux of that fermion parity symmetry through the hole of the ring. So I can go from Neveu-Schwarz boundary conditions to Ramon boundary conditions in field theory language. So I can put a flux equal pi through here. Okay, so let's see. I only need one copy of my wire, so let me erase the extra copy. Okay, so here is a wire cut open. Now let me imagine gluing the ends together, right? Okay, so I can glue this Majorana to this Majorana. Okay, so that's going to put on an H, let me call it N1. Okay, so if I just use periodic boundary conditions, then I go I, gamma N bar, gamma 1. Okay, so this is periodic boundary conditions, so this is basically Ramon. If I use anti-periodic boundary conditions, I use the other sign, never Schwarz. Well, in both cases, this gaps out the two Majoranas, right? So here the ground state has I gamma n bar gamma 1 equal to -1, and here ground state has I gamma n bar gamma 1 equal to 1. But remember, we saw that for the chain, if I look at the Fermat parity of the entire chain, that essentially collapses to just this product of the boundary Majoranas. So that means that here my Fermat parity is exactly -1, and here Fermat parity is equal to +1. So we see that as we thread flux pi through the circle, as we change from Never-Schwarz to Ramon, the Fermat parity of the ground state flips. So this is a way to diagnose the Kitaev wire already on a closed manifold without cutting it open. And we'll see that this will be the general story for invertible phases, and also invertible phases with symmetry. You would be able to distinguish them already on closed space-time manifolds by thinking about insertions of either symmetry fluxes or Fermat parity fluxes, or just taking the space-time manifold to be non-trivial. Okay. Right. So far everything has been on the lattice. Now let's see how to take the continuum limit of this Kitaev wire. How to represent it by a field theory. So continuum field theory. So let's see. So again, the draw on top of here. So here is my non-trivial wire. Here is my trivial wire. Let me imagine that I tune my Hamiltonian from this one to this one. So let's consider h 1 minus lambda. So this is the Hamiltonian for the trivial wire. So we already, I hope I already convinced you that this have to be in different phases, right? For instance, this bulk diagnostic about Fermat parity flipping under flux insertion, that's like a invariant that distinguishes the two phases. So there has to be a phase transition as we tune lambda, right? So lambda equals 0 is trivial. Lambda equal 1 is Kitaev. There has to be a phase transition, at least one phase transition, as we tune lambda from 0 to 1. And in fact, the phase transition occurs at lambda equal to 1/2. Phase transition. When lambda is equal to 1/2, if you kind of graphically represent this, then all your Majoranas, they're kind of completely undimerized. You have equal couplings. Equal strength couplings between all the Majoranas. Kind of looks like this. All the couplings have strength 1/2. If I go on a and I can close up if I want to be on a circle. Okay, so what is the spectrum there? Well, this is just a free Fermat problem. So you can solve it by going to momentum space, and the dispersions that you find are the following. Ek, so let momentum go from minus pi to pi. You find this dispersion at lambda equal 1/2. So you have one right moving mode. So this is zero energy and zero momentum. And at that point you have one right mover and one left mover. And because these gammas are Hermitian, these are Hermitian right mover and left mover. So you get, if I take the continuum limit, focusing on the neighborhood of k equals 0, which is the low energy mode, so linearizing near k equals 0, we get the following Hamiltonian: dx chi right, one right moving Majorana and one left moving Majorana. Chi right x dagger is equal to chi right of x. And usual canonical anti-commutation relations, right? So this is an Ising CFT. Ising CFT with C right equal to C left equal 1/2. What happens when we tune lambda away from this special point of 1/2? Can anyone guess? Well, that's right. You give a mass to the fermion. Lambda away from 1/2. Delt H equal to I m chi right chi left. So this will gap out the system, right? We'll do something like this, and for one sign of the mass you get the trivial phase, and for the other sign you get the non-trivial. Okay, it's a bit a matter of convention which one is trivial and which one is non-trivial. Let's take the m less than 0 as the non-trivial. Okay, so how do we now understand this edge? So far we did everything on a circle, closed circle, right? We had this dispersion as a function of momentum. How do we understand the Majorana modes in the non-trivial phase? Well, actually in a way that's exactly analogous to what Tom discussed last week. Remember the domain wall fermions? Oh. Understanding boundary Majoranas. So first of all, we can think of if I have a segment of a Kitaev chain like I have it here on the bottom line, I can think of this not as a finite piece of the real line, but I can think of this on the entire real line, where on the complement of this segment, I just have a very large or small? Yeah, on the complement of the on the complement of the chain of the segment, I just have lambda equal 0. So all the Majoranas here, all the Majoranas here have lambda equals 0, and similarly on this side. Right, so I can think of this boundary as simply an interface between the Kitaev chain and the trivial chain. Right, I still have these dangling Majoranas left over then. So let me now model this in the continuum. Well, in the continuum, this each boundary then will correspond to a domain wall of M as a function of x, switching from positive to negative. And if you just go ahead and you solve the Dirac equation in the presence of such a spatially dependent mass, you'll find 0 modes localized at each boundary, as Tom discussed, and as was perhaps first discussed in the context of polyacetylene. So have 0 modes here, 0 modes, localized here. And those will be exactly the Majoranas that appear in these idealized chains. Okay, so we see that we can reproduce a lot of the, well, essentially all of the physics in the continuum. But now, once I'm in the continuum, I can do more. Now I'm really liberated to, first of all, write this in a Lorentz. This now has a emergent Lorentz symmetry. Let me write it in a Lorentz invariant notation, where these chi's are now two-component Majoranas. Each one is essentially chi right, chi left, and there is some choice of gamma matrices, and okay, there's some choice. You can work it out. But now that this just becomes a massive two-component Majorana, so I can now couple it to a curved metric, and I can consider this theory on an arbitrary Euclidean two-dimensional manifold. Let's see. Consider a theory on general 2D Euclidean manifold M. Okay, so I trusted that all of you can covariantize this properly, put it in curved space, but let me call, once you go through all the bells and whistles of doing that, this becomes some Dirac operator D, and let me call this combination C star times D plus M, let me call that just D. Okay, so it's a Majorana, right? So this D will actually be antisymmetric, better be antisymmetric, and if I calculate the partition function of a Majorana like this, what do I get? For fermions, for complex fermions, what do I get? For partition function. It's a free theory, right? No interactions. For complex fermions, I get determinants. For real fermions, I get Pfaffians. So I'll get this Pfaffian of this D. Pfaffians are a real pain to deal with, because what is the sign of the Pfaffian? It really depends on how you order the order your vectors. So morally, phi n is a determinant, is a square root of a determinant. But choosing the sign is tricky. However, in this case, we are in a pretty good shape. And the reason is the following. Picking the sign of the phi n is tricky. But if I have a family of operators, then I pick the sign once and for all for at some initial point of the family, and then I just continue analytically. So in this case, let me pick the sign when m is positive and very large. Right? When m is positive and very large, I know that I have a trivial product state. Right? That's my trivial Kitaev chain. So for a trivial product state, I expect m goes to plus infinity, expect that my partition function will be just 1 up to terms that can be removed by counter terms. Remember, as Roma talked in his first lecture, there are these terms involving the curvature of the manifold that you can remove by counter terms. So up to local counter terms. Okay, so this will fix my the sign of my phi n for m going to plus infinity, and then I can calculate this ratio z of m over z at infinity is completely well defined. In particular, I can just focus. Let me just focus. Well, so this is well defined. I'm really just interested in what happens in the non-trivial phase when the mass goes to minus infinity. So really, I'm just interested in this ratio, z of minus m over z of m. Turns out that this is m independent, and is equal on a closed manifold to -1 to number of zero modes of this Dirac operator D over 2. Closed manifold. This is important. So, couple of points. First of all, there is no need to worry, because this number of zero modes of the Dirac operator is always even. So this is just the partition function is always plus or minus 1. Remember, we said in the beginning that we expect the partition function of an invertible theory on a closed manifold to be a pure phase. Well, here it's a pure phase. It's plus 1 or minus 1. Okay. Furthermore, it's a topological invariant. So first of all, let me write minus ID over 2. This number of zero modes of the Dirac operator. This is the same as number of zero modes of, say, chirality plus 1 Dirac operator, where remember gamma bar is just I, gamma, not gamma. number of zero modes with gamma bar equal +1 in this case is the same as number of zero modes with gamma bar equal -1. That's why the total number is even. So turns out that this quantity is a mod 2 topological invariant. Mod 2 invariant. The reason is that first of all, so let this be equal 0. Well, I don't know, E. How should we denote eigenvalues of this Dirac operator? Let's denote them by mu. So this is mu equals 0. So as I already said, so first of all eigenvalues of Dirac operator come in pairs because this charge conjugation operator squares to -1. So okay, so actually all levels, not only zero modes, are doubled. Moreover, because gamma bar anti-commutes with the Dirac operator, all positive energy levels come in pairs with negative energy levels. So now, this becomes completely analogous to what Clay discussed last week for the Witten's index. You imagine you change some parameters of your manifold, such as the metric, smoothly, right? So some of these finite energy modes can come down onto zero energy, but they always come down in multiples of 4. 2 from above, 2 from below. So then I divide over 2, I get 2. So this is mod 2 index. Tom?
So is this all because you have Majorana fermions and the eigenmodes are paired in general, or is it because you have a closed surface and so you always get, I don't know, left-handed and right, an even number of zero modes? Or is it both of those?
It's both of those. It's specific to. So the question was about these doublings, both in, I guess, positive and negative energies, and also for each energy. So depending on depending on dimensionality. So first of all, So first of all, note we are in space-time picture now. So these are modes of the space-time Dirac operator, not spatial Dirac operator. So if I was solving some Bogolubov-Dejean equation, which is just in space, then always positive energy modes come together with negative energy modes. But this is in space-time. So it turns out that, for instance, if you consider this on a non-orientable manifold, then this is no longer true. The positive ones and the negative ones don't come in pairs. The doubling, the ck squared equal -1, also, I don't remember exactly, but these things vary depending on dimension. But and in some dimensions you'll get integer indices, in some dimensions you'll get mod 2 indices, so you have to be careful. Okay, so we see that this is a topological invariant, mod 2 invariant. It's actually stronger than that. It's actually a Bordism invariant. So I think Bordisms were mentioned briefly in the first week. So let me define what the concept of Bordism is. Bordism invariant. Two manifolds, M1 and M2 of dimension D are bordant if there exists a third manifold M3 of dimension D2 closed manifolds exist M3 of dimension D plus 1, which interpolates between them. Right? So here is M1 is a disconnected sum of two circles. Here is M2, which is a single circle, and we see that there is so each one of both M1 and M2 have dimension 1. There is a two-dimensional manifold, M3, such that M2 and M1 can appear on its boundary. So such that D M3 is equal to M1 disjoint union M2 bar, where this stands for orientation reversal. Okay, so our
What would be a simple example of some manifolds that are not ordered?
what are examples of manifolds that are not bordered? So so say if we allow non-orientable manifolds, the simplest one is RP2 is not a boundary of any three-dimensional manifold. If you want to have with orientation, then CP2, a four-dimensional manifold, is not a boundary of any five-dimensional manifold. And we'll see another example with spin structures in a second. So claim so now we are dealing with closed two-dimensional manifolds. So my claim is that this quantity is a Bordism invariant of two-dimensional manifolds. That is, if M1 and M2 are bordant, then Z of M1 is equal to Z of M2. There is one subtlety here, which is that I'm talking about fermions, right? And for fermions, when I put them on manifolds, there is something that enters. That's the spin structure, the boundary conditions. So more precisely, if M1 and M2 are bordant as spin manifolds, which means that each one of them comes with its own spin structure, and there is some way to to continue the spin structure onto M3 such that everything is nice and smooth. So if this is the case, then the partition functions have to be the same, right? So it's a stronger notion than just topological invariance. And this quantity does have that property, and in fact it's the content of Attaya-Patodi-Zinger type theorem that this is a Bordism invariant. APS theorem. Okay, so actually I'm kind of working in vacuum here. I didn't tell you of any manifold for which this Z is non-trivial. So turns out that consider the following manifold. Consider a torus, two-dimensional torus, with Ramon boundary conditions on both cycles. Then for this manifold, Z is equal to -1, And for all the other boundary conditions on the torus, ns equals z nsr equal to z r ns equal to 1. Yes?
Say boundary conditions, you mean the spin structure?
Spin structure, but yeah. So now take home exercise. Check that this is consistent with what we found on the ring. Remember we took a ring with threaded flux pi. We saw that fermion parity switches. This is the same observation, exactly same statement. Now, why is this manifold special, a torus with Ramon-Ramon boundary conditions? Well, it turns out that so I defined the notion of, so turns out that spin Bordism group in 2 dimensions is generated by this manifold. So just like with invertible phases, we had an addition operation. There is also an addition operation that turns Bordism into a group, where addition of 2 manifolds is simply the disjoint union. So that turns Bordism into an abelian group, and right. So Bordism abelian group under disjoint union, where elements of this group are just equivalence classes of manifolds, where the equivalence relation is Bordism. Okay. And right. So it turns out that in 2 dimensions, torus with RR spin structure generates the spin Bordism group, omega 2, so abelian group under disjoint union, omega d. It's called point. Disregard this point for now. Here, this can be a spin. This, for fermions, I would say spin. That's if your Bordism has to respect spin structure, or maybe it has to respect orientation, then you would say SO. So yeah, disregard this. It doesn't really matter, but generates the spin Bordism group in 2 dimensions. Right. So every 2-dimensional manifold with spin structure is either Bordan to this torus with RR spin structure or Bordan to a point. Okay, so then I only have to say what my partition function, what values my partition function takes on for those 2 manifolds. Well, for a point, better take on value 1, and for this one it picks up it takes value -1. Right. So okay. Now the belief is that this is not a coincidence. In fact, the belief is that all invertible phases can be classified by Bordism. Belief all invertible topological field theories are characterized, are classified better. Yeah, let's say, so remember the group, let me call GD the group of invertible topological field theories. The belief is that torsion of this, it's an abelian group, right? So, it's going to have some finite factors like Z2. Like in this case, or it can have some Z factors. So the torsion is the is the finite part, Z2, Z3, Zn. So the belief is that torsion of this group is exactly the same as torsion of, well, is isomorphic to torsion of the Bordism group in the same dimension. And the free part, the factors of Z is the same as, well, basically this is Chern-Simons, gravitational Chern-Simons terms. CS terms. And this is governed by the free part of Bordism group in one high dimension. If this is too formal, don't worry about it. It will not appear anywhere else in my lectures. Yuji might talk about it next week. So this is essentially, I would say, Kapustin, Fried, Hopkins are the right names to mention here.
The Bordism group always shows it to respect spin.
Pardon me? So if you're talking about phases of fermions, you have to consider spin Bordism here. If you're talking about phases of bosons with no other symmetries, then this has to, with respect to orientation, SO. So it has to, you have to preserve orientation all the way through your Bordism.
So I guess when we define Bordisms here, we could say we have manifolds, but we also want to consider additional structure. And whatever additional structure we're interested in, we have a kind of Bordism that preserves that structure.
Exactly, yeah.
Is it always a Stiefel-Whitney class?
Well, is the question, so let me repeat the question. Is the invariant always a Stiefel?
Or rather, are these things always sort of preserving a Stiefel-Whitney class in their sort of Bordisms? Or can you generalize it to like spin C structures?
So we might talk about spin C structures when we talk about U1 symmetries. So for this is an example where an invariant is clearly not a Stiefel-Whitney class, right? Because, well, first of all, Stiefel-Whitney classes don't depend on spin structures. So when we have fermions, clearly Stiefel-Whitney classes are not enough. For bosons, when we talk about, Stiefel-Whitney classes are only Z2 numbers, right? If we want, I'm saying sometimes I have a free part, so then I need also these gravitational Chern-Simons terms. So
I just mean that to have to be a Bordism invariant, you also have to have them be sort of equivalent under sort of, as you say, spin manifolds or say orientable. Let's say when your superscript here on this gamma D, you have a Stiefel-Whitney class up in the superscript.
So you're correct. The Stiefel-Whitney classes are Bordism invariants. So it has to preserve that. Yes.
Can you actually elaborate what do you mean by invertible TQFT?
So the question was whether I can elaborate what I mean by an invertible TQFT. I defined invertible phases I defined invertible phases last time. So an invertible TQFT is a TQFT that arises from an invertible phase. that is a low energy topological field theory describing an invertible phase. If such a topological field theory exists, I'm sure then the content of this paper by Fried and Hopkins is to define this. So this only gives the partition functions of the topological field theory. The content of this paper was to define the theory as a fully extended topological field theory. So I think that paper should satisfy you. Other questions? All right. Let's see how we are doing on time.
About 25 minutes.
Okay. So far we only discussed in this continuum limit on arbitrary manifolds. We only discussed the theories on closed manifolds. So what happens on manifolds with boundaries? Now what happens to those boundary Majorana modes? Let's see, what can we erase? I don't want to erase this. What happens on a general manifold with boundary? Okay, so we already know that there should be just a 0 plus 1 dimensional Majorana living on that boundary. So what is the action for the 0 as boundary? What is the action for the 0-dimensional Majorana? Well, it's chi d tau chi d tau. Not a very interesting action. So the boundary partition function then, again, this is a Majorana, so it's real. So z boundary, just acting, being very naive, should be Pfaffen of d tau. But now again we run into this. Okay, d tau is antisymmetric, at least that's good. But we run into this problem that we have to define the sign of the Pfaffen. And now we're really in trouble because we don't know, there is no reference point to define this with respect to. There is no mass term that we can write down and say that for one sign of the mass we're going to define this as 1. So which sign? Which sign? Furthermore, if I consider this boundary to have okay, so first of all, one-dimensional manifolds are all circles, right? But I can have Neveu-Schwarz or spin structure or Ramon spin structure around that circle. If I have a Ramon spin structure, I'm going to have 0 modes. Okay, so then this Pfaffen is going to vanish. Well, thanks God. We don't have to worry about sign of 0. But we might want to compute correlation functions, right? And in those correlation functions, well, it's a Grassmann integral, right? So there are going to be some 0 modes. So if it's Ramon, say Ramon here and Ramon here, you have some 0 mode nu1 and 0 mode nu2, and I have to do Grassmann integration over these 0 modes. But the question is, what is the sign of the measure? Which order? What nu1 to minus nu1? So I should be able to answer all of those questions. And there is no way to answer those questions within just this 0 plus 1 dimensional theory. So this is anomalous. But so the answer is that really you should put this together with the bulk partition function. Well, okay, so here was our bulk partition function, which we defined for closed manifolds. It was related to the number of zero modes of this Dirac operator. But now I'm on an open manifold, so I have to say what boundary conditions I have to put on that. I have to. Yeah, I'm trying to make sense of this on an open manifold, so I need some boundary conditions for this minus I d slash. Turns out the right answer is you need to use non-local Ataya-Patodi-Zinger boundary conditions, and then this quantity z full times minus 1 d slash with APS boundary conditions makes sense. So individually, these things will not make sense. Well, the non-locality of the boundary conditions that we have to use here would be bad if you don't put in this Pfaffen factor from the boundary. So this thing by itself also doesn't really make sense as we discussed. But altogether, we get something sensible. Right. There's actually a recent paper on this by Dijkgraaf and Witten. Apparently, this also has something to do with two-dimensional gravity, but I'm not in a position to say more. Any questions? Uh-huh.
So does this sort of thing happen for all of these, I guess, is this general for all of these interval TFTs? Where I have like some, I don't know, I guess product of boundary partition function and bulk partition function?
Could you repeat the question?
The question was how general this is. So in general, we'll have some bulk partition function, and we'll have trouble defining it on a manifold with a boundary, and we'll have to put some theory on the boundary to make sense of it, some non-invertible theory on the boundary to make sense of it, which would mean that the boundary cannot be trivially gapped. Other questions? Yes?
Is it always like this APS boundary condition, for example, if you have
No. So this is so I have a list of so the question was whether this is always going to be just APS boundary conditions. So that's going to be the case for free fermions, but there are phases beyond free fermions. So let me very quickly summarize what we've learned here. I'm just going to read this off. So we have a distinct gap phase, this Kitaev phase in 1+1 dimensions. It has a unique ground state on a circle. It has an anomalous edge. The anomaly is that there is, the fermion parity operator. In the lattice language, the fermion parity operator fractionalizes into two Majoranos acting on the boundary. We can think of the bulk as determining the anomaly of the boundary. That's why the anomaly cannot renormalize. We can characterize the phase without looking on the boundary. We can characterize it already on a closed, for a closed system by considering insertions of fluxes, or in other words, non-trivial spin structures. Partition functions on non-trivial manifolds with different spin structures give some interesting topological invariants. So far, all of this, if you look at this, at the Hamiltonian that we used, it was a free fermion Hamiltonian, so going back to your question. Turns out that classifying such free fermion Hamiltonians, it's a problem in band theory, right? You just you go to momentum space and you look at what kind of how your wave functions look over the Brillouin zone. And turns out that's a problem in K theory, and it has been completely solved. And it's very useful for experiments because many materials interactions are not very important. So then you can really make predictions. Someone tells you the structure of your material, how many, I don't know, indium and antimony atoms there are in each unit cell. And you look at the electronic structure, you can predict, and you can see whether it's topological or non-topological. But this classification, this free Feynman classification, this way of thinking is not very useful for thinking about interacting systems. What is true is that for all of those free Feynman phases, when you take the continuum limit, you're going to get some number of Majorana fermions or some number of Dirac fermions, and the partition function is going to be on a closed manifold is either going to be some -1 to the index or the ET invariant, the spectral asymmetry. So that's actually very general for these free Feynman phases. Ataya-Patodi-Zinger theorem is at work in all of this. Yes. So these are the lessons. Now, one more thing I wanted to mention is that actually a lot of people are interested in these Kitaev wires because actually there are claims by several groups that they've been realized in experiments, and people go ahead and study them. So the kind of systems are indium antimony and indium arsenic nanowires, and also iron chains on lead. But let me. And people are hoping to use them for quantum computation because you have kind of this non-local way of, they have this non-local degeneracy. But let me not say anything more about that. If there are no questions, let me very quickly tell you about other invertible phases in low dimensions. Okay, so I have to distinguish between phases of bosons and fermions. Let's see how we do this. Bosons, fermions. Dimension. So 1 plus 1, 2 plus 1, 3 plus 1. Okay. Let's be generous and put 4 plus 1. So first, let me say what the classification is. Remember, this form an abelian group. And then let me say what the partition function is. So class. Yeah, I don't know. Also had something called generator. Generator Z. Then class generator Z of M. Okay, so this is one that we determined, right? So this is the boson-fermion boundary. For fermions in 1 plus 1 dimension, we said that there is a Z2 classification. The non-trivial phase is the Kitaev wire. The partition function on the closed manifold was this thing actually is also known as the ARF invariant, or this is equal to the ARF invariant that depends on the spin structure. Okay, for bosons in 1 plus 1 dimensions, turns out that life is boring. There are no non-trivial invertible phases. In 2 plus 1 dimensions, there are invertible phases for both fermions and bosons. For fermions, the classification is Z, and it's generated by what's known as a P plus IP superconductor. And the partition function is the gravitational Chern-Simons term. Let me very quickly say what this phase looks like. Again, it's a free it can be realized with free fermions. The easiest thing to say is to say what its edge looks like. The edge is a single chiral Majorana, say chi right, with central charge right equal 1/2, central charge left is equal to 0. This is one. In fact, yeah, anything with the chiral charge difference would 1/2 would work. Bulk, you can think in terms of a two-component Majorana in 2 + 1 dimensions, P slash plus M chi with inverted mass. It's very similar to what we had in 1 + 1 dimensions. Once you integrate this Majorana out, what you get is you get this gravitational Chern-Simons term, which can be defined as follows. Chern-Simons gravitational is 2 pi I 1/16 1/24 pi squared x4 trace R wedge R, where here is our 2 + 1 dimensional manifold M. We have to extend it to a 4-dimensional manifold X4, extending the spin structure also because we are talking about fermion theories. And we have to compute this trace R wedge R over this open 4 manifold. That's the gravitational Chern-Simons term. This is not going to be metric independent. This is going to depend on the curvature of your boundary manifold M. This is roughly something like trace omega wedge d omega plus 2/3 omega cubed, but you know it's not exactly. This is kind of perturbative. It's independent of this X4 because on a closed manifold, this 1/24 pi squared trace R wedge R of a closed manifold is the signature of the closed manifold. Well, for an arbitrary closed manifold, the signature is an integer. For a spin manifold, the integer, for a smooth spin manifold, the signature is a multiple of 16. That's why I have this 16 here. That's why this is well defined, up to multiples of 2 pi I. Similar to what Greg talked about in his lectures. Okay, so this is this point.
What's the comment about being perturbative? The second gravitational Chern-Simons, as you've written it in terms of the spin connection, what's perturbative about it? Why I'm just here? If there's no obstruction to going to 4 dimensions, in extending the gauge field, then why is it not the same? I mean, there could be additional terms, but what's perturbative about it?
The point is that the variation of this is essentially something of this form.
Yes.
But itself,
Sure, because you're in 4 dimensions, so you can write a Chern-Simons term anyway. But the lower thing is not on M. That's in 3 dimensions.
that's right.
Yeah.
That's right.
Right. So I didn't get the point about the perturbativeness. You said it's not the same. It's not this. It's more stuff.
I think you have to be a little bit careful because you need a framing here if you want to define it. So there are all those. So this is the statement that I'm confident about is that if you integrate this Majorana out, then what you get is this. I think there are extra subtleties that you have to worry about. But we can discuss afterwards.
Is this family SON level 1 in some language?
That's right. Yeah. The question was whether this is SON level 1 in some language. And the answer is yes. Other questions? So one comment I want to make is that, well, okay, so first of all, the boundary is anomalous. A field theorist would say, well, there is a gravitational anomaly. When you try to put it in curved space-time, that has to match the variation of this thing when you have a when you have an open manifold. This is, the integral of this is not going to be invariant under diffeomorphism transformations. That's one way of thinking. There is a much simpler way of thinking. You cannot have in 1 dimensions, in 1 + 1 dimensions, you cannot have a chiral theory. At least you cannot have a chiral theory emerging from a lattice. There is a very simple argument for that, which is completely non-rigorous, but let me give it still. Cannot have a chiral theory emerge from a lattice in 1 + 1D, no matter what you do. The argument is the following. Let's compute in a chiral theory, let's compute the energy current at finite temperature. Well, this is kind of like computing the energy on a circle. And, well, for the energy you would get plus, but for the energy current you get minus. So this is proportional to the chiral central charge. Now, okay, so this is some bulk quantity. I have an energy current everywhere in the bulk. Well, if I put this on a circle, if the spatial manifold is a circle, it's okay, because the heat just circulates. But what if I have an open segment? What happens at the end? This is some bulk computation. It can't be changed by altering the boundary conditions. So where does the energy flow? This is an equilibrium, after all. So you cannot just have energy building up here. So there's some big problem with this. Okay, maybe this argument is bogus, but there's actually a proof that you cannot have a energy current in 1 dimensions found by Kapustin recently. So this tells you that any chiral theory cannot emerge from a lattice in 1 + 1D. So the edge is anomalous, as we promised. Okay. Am I out of time?
You have 2 minutes.
Very good. So let me complete this table. Bosons in 2 + 1 dimensions turn out to have a integer classification. Also, generator is a so-called E8 phase. Partition function is exponential of 16 times of this. Edge theory is going to have 16 times the chiral central charge, which is 8. E8. So the boundary, L boundary, is something like this: I over 4 pi d I dx phi I k I j dx phi j plus kinetic terms. Let me schematically write them as dx phi squared, where k is the Cartan matrix of E8. It's an 8 by 8 matrix. Carton matrix. Of with determinant 1. And all eigenvalues having same sign. So this is going to give rise to chiral, this is going to be chiral with chiral center of charge equal to 8. Okay. So yeah, gravity and the bulk partition function is the same except 16 times that, because now we don't have spin structures anymore. So when we extend, we can only use the fact that that signature is an integer, not a 16 times an integer. So we cannot use this 1 over 16 here. We have to use 1.
Are these churn insulators or?
This one is a P plus IP superconductor. If you take twice, you get the integer quantum Hall effect. And the bosonic ones are bosonic ones, right? So they're not made out of fermions. The churn insulator. So the question was whether these are churn insulators. And I'm almost done, because in 3 plus 1 dimensions there is nothing, and in 4 plus 1 dimensions you only have something for bosons, and the generator doesn't really have a name, and this is the action. It's written in terms of the Stiefel-Whitney classes. I have little understanding of this phase, so I won't say anything about it. Let's stop here, and we'll talk about symmetries next time. Yes?
As for the earlier question of why it's not completely legitimate to sort of use Stokes' theorem and go from R wedge R to the Chern-Simons term, I think the reason is because of the 1 over 16. So it's essentially like in the parity anomaly case, where in that case one would integrate out to the fermion, and then one usually says that this induces half integer shift of the Chern-Simons level. But the reason that it's an anomaly is that that sort of Chern-Simons term with half integer level is actually not local, so you can't remove it with any local counterterms. So really a Chern-Simons term with half integer level doesn't make any sense until you extend it into a 4-dimensional manifold. That's why really you should be doing that in terms of an 8 invariant, which takes into account this extra convolution from the index of the Dirac operator in the 4D space that cancels out that non-locality.
Yes, it's just that the question was an answer to why you cannot use this, the answer invoked the APS theorem for this quantity, which says that the boundary partition function, the partition function of this is basically related to the eta invariant of the chi's, and the APS theorem says that this is related to trace R wedge R plus an index of the bulk Dirac operator, and you're saying that that index is non-zero, so there is an ambiguity of there is some sort of discrete ambiguity of this thing, and that's correct. There is another kind of way of thinking about it, which is that you can always choose a framing on a 2 plus 1 dimensional, on a 3-dimensional manifold, but somehow this thing determines a canonical framing. Yeah.